Okay, so IMRCE stands for Immersive Mixed Reality Collaborative Environment. But let me tell you a history, and how we ended up to design this toolkit. As you know, collaborative environments are very famous in HCI, in CSCW. There have been a lot of research going on about the collaborative environment, like screen sharing, desktop sharing, using teleconference, and there has a long history. Also using virtual reality, virtual environment, it has also a long history in CSW and HCI. Many research from 90s started and it's still going on. But thanks to new hardware like HTC Vive, Oculus Rift, HoloLens, they become trending again, and new research and the amount of research, the number of research is still start increasing again due to this new hardware and the power they have. Two of the important concepts in collaborative environment are the awareness and the presence. If we want to have an effective collaboration between the people, between the collaborator, we need to help them to feel co-presence with the other participant, especially when they are not in the same place and they are in a remote location. Also, we need to help them to increase their awareness. They know what's going on, who's talking, who's working on the task, or who's like taking a turn for working with the, like, for example, 3D objects. So we were interested to do research in the focus of awareness and presence in a collaborative environment. And we decided to design an environment for that. To explain the environment, we wanted to have some people stay in one co-located location around the touch tabletop. In the same time, we wanted to have some collaborator. They are being in a remote location and they connect to the co-located using a VR headset like a Oculus or a HTC Vive. We designed this environment. Let me show you some screenshot of that. This is the co-located location. You can see two co-located collaborators standing together around this touch tabletop. They can work on the objects, rotate them, scale them, zoom in, zoom out. Also, we had a remote person standing another location and could connect to this person. So the remote person could have a headset on his face, connect to the virtual environment, and start collaborate with the co-located people. There is another screenshot from the remote person when he or she is working inside the virtual environment and collaborate with the co-located. I also have a short video show you guys how the co-located people work on the tabletop, touch tabletop. So you see they can work around this table, they can freely walk around the physical tabletop, and as if you notice there is a hand coming onto the table. This is the hand of the remote person. When he's working inside the virtual environment, the co-located can see his hand or her hand. Also, I have a video from inside the VR environment. Yes. So as you see, the remote person put a headset on, connect to the virtual environment, and he or she will work with the co-located in the same time. And he can use his hand. Also, he can see the hands of the other person, the hands of the co-located people when they are working around the tabletop, the physical tabletop. So we designed this environment for our study, run our study, and after that we decided to, after we finished the study, we noticed that we had a lot of difficulty to design this environment. It took us a lot of time to put all the libraries together, to develop the algorithm, and the main reason was we didn't find any toolkit that helped us to develop this environment, to develop this mixed reality collaborative environment. So we decided to put all these libraries and this algorithm together and offer them as a package, as a toolkit to the community, so people won't have the problem we had, and they can develop this type of environment in a shorter time and faster, and they just get to the research and do the research. So our toolkit helped the community developer to prototype an immersive mixed reality collaborative environment. This means they can develop this like just for tabletop, touch tabletop, or just for VR, or for both. So it helps people, collaborators, to work with each other, regardless they are standing around the physical touch tabletop or wearing a headset. They can work on the same object. This toolkit will help people to reduce the time of programming, so they can rapidly prototype the immersive environment they need. Also, it collapses the complicated process of designing those type of environment to very simple steps, just like dragging and adding those features they need to in the environment, and the minimal amount of programming. If they need just new, maybe gestures, they need to just program those based on the basic we put in the toolkit. So the Immerse toolkit offers 5 main parts. The first one is setting a client and server application. As I said, this is a collaborative environment and it's supposed to connect remote and co-located people together. So we need a client and server application. Also, they can design an application for the touch tabletop and design the desired gestures. Right now, we are supporting for translating, for rotating, for zooming, zoom out, for lifting the object on the environment, and for rotating the objects. Also, they can add the hand tracking. As you saw in the videos, developer can add the hand tracking to their application. Right now, we are supporting lip sensors. We are working to add the other, like the handset of the hand controller of HTC Vive and Oculus Rift, but for now, it's working with the lip sensors. Any position tracking system that can communicate with the OSC, Open Sound Control, can also communicate with our toolkit. So regardless of what's the position tracking, if it can use the OSC, it can communicate with the toolkit and have the position tracking. For this toolkit, when we are putting on a GitHub, we have a link to our own position tracking system, which we developed in our lab. We call it DT. Feel free to have that with your system. Very great position tracking systems. And also, as you see, we can have the VR clients if you want to. They work with the co-located people on the touch tabletop. Very simple sketch of the toolkit, how it works actually. So in simple words, there are client B, client A. They can be both VR or touch tabletop users. There is a server. The server will spawn the 3D shared objects, also the hands, and they will be synchronized on the both clients. And the server also has the responsibility to change the ownership of the 3D objects between the clients. So the developer, they don't need to be worried, oh, who's working with object, how should I detect if he or she should change it or not. The server take care of those ownership and transferring them between the clients. How to work with the toolkit? It's very easy. We developed this for the Unity right now. Hopefully in future we have a version for the Unreal Engine, but for now it's developed for Unity. By importing the package to the Unity, you will have a new tab on the menu. It's called IMRCE, and from that you can have access to different features of the toolkit and add them to your program. For example, if you need to set up the custom network, you just go to the tab, to the component called the IMRCE, and add the network to your application, and that's it. The server technically ready. So, you know, we are researchers, so just design is not enough. So we evaluate this toolkit to become sure actually it helps the community and the developers. So how we did that? We used the A/B comparison. We had 10 participants, 2 groups of 5, and they worked on this toolkit about 10 hours over 2 days. We have 2 female, 8 males. They were between 21 to 25 years old, and they were also familiar with the Unity programming. They had the course before, so we consider that. For the setup, we use the Rift, the Oculus Rift head-mount display. We have the gaming desktop, so people could try their applications after developing with that gaming desktop for the headset. Also, all of them use their laptop. Regardless, we had the computer set up for them, and we asked them if they like to use it, but everybody preferred to use their own laptops. As I mentioned before, we use the DT position tracking system for tracking the location of people in the environment, and it's connected to the toolkit using the OSC. We use a physical tabletop for testing again, and lip motion sensor. All the participants had the lip motion sensors, all 5 of them, each of group. And we had 2 touch Windows Surface again for testing the application. So we designed two conditions. In the first condition, we ask participants to use the IMRCE toolkit, and the other condition, we give them a set of libraries and we suggest them they use that, not the IMRCE. So that was the second condition. And in one day they use the IMRCE, and the other days they repeat the task by not using the IMRCE, and we counterbalance between them, of course. So the collaborative, the task was actually, we asked them to design a collaborative environment that connect 3 remote participants to each others. One of these participants supposed to have a headset, one of them supposed to work on a surface, Windows surface, and one of them supposed to work around the touch tabletop. And this environment should have hand tracking and also position tracking. This was the task. And these 3 people should be able to work with each other and assemble a car from its parts. So we always have a researcher in the environment working with other collaborators. He was taking notes, answering the questions. We use demographic and post-conditioner questionnaire. We have a short semi-structured interview after the study. And also we time each of the tasks. So they have a limited time for developing each of the tasks. For the analysis, we had the usability analysis. We followed the suggestion come from the Leodo paper. Very nice paper. It's a CHI 2018, and it's a survey on Toolkit and how to evaluate the Toolkit. I suggest look at that paper. Very help us to come up with the right way for evaluating our Toolkit. So we had 5 parameters: the time took the participant to complete the task, the level of completion, number of line of code and the questions, and number of the problems they had. Well, also we normalized the number of problems by dividing that on the number of line of code they had. For this, we used the paired sample Ttest. As you see, it was significant in most of the part, like for time, level of completion, number of line, it was significant, and all in favor of the IMRCE toolkit. We also had, as I mentioned, post-questionnaire, and for the study and semi-structure interview. For the post-questionnaire, we aimed for 2 basic statements: satisfaction with the result for each steps, and also satisfaction with the toolkit used for each steps. So for the first one, we had the result. We also run the Wilcoxon test, a non-parametric test on the results. And we had the significant difference in most of the parameters, in 3 of them actually, in favor of the IMRCE toolkit. And for the other one, we used the Wilcoxon, but we didn't have that significant for the toolkit. It's very similar in terms of the result. So in terms of the contribution, first of all, we have a toolkit that helps the community for rapid prototyping. We test this, we have an evaluation, and it shows us, yes, it's improved the number of the time they are developing. It reduced the time and also reduced the number of questions and problems they had. So IMRCE actually allow you to develop application to run it on different devices. It can be a Windows, it can be a tablet, it can be a Surface, it doesn't matter. And that's actually one of the reasons we use the Unity as a base platform for us, because you can compile application for different operation systems. IMRCE allow you to efficiently match the different screen with each other. So if somebody working on a big tabletop and somebody working on the Windows Surface, there should be a mapping between the objects. So you don't want to have a big size on the tabletop and the same size on the Surface. So IMRCE actually does this mapping and allow you to have a right sizing between the different windows. We are providing support for synchronizing the virtual hands between the collaborators. So if I'm co-located working on the touch tabletop and I bring my hand on the table, performing different gestures, in the real time we detect this, we synchronize this movement and gestures on all the clients, and they can see the hands, the gesture I'm making, and vice versa. Of course, there were some limitations when we were working on this toolkit, when we are developing this toolkit. So one of them was, so participant came, we have a training for them to, same training for all of them to learn how to work with the toolkit and with the libraries. So we know that it was less likely when people start using a library and they find out it's not good, they less likely to switch something else because of the limited time they had. So that was one of the limitations. Also, they had a limited time to go and look at the API for the libraries they supposed to use in the non-immerse. So we suggest the library, we had a short training, but still people sometimes need to look at the API, and we know they had a short time to look at that. Another deal is the calibration. So when you are working with the sensors and you are tracking hands or position, you always need to have a calibration based on the physical environment you are in and you are working on. And the reason is that, first of all, the environmental setup, like a lighting, like the objects, and the second one, the size of the environment. So that's another limitation we have on the toolkit, so researcher and developer need to take care of that calibration. And also, as you know, the facial expression is important part for collaboration environment, and it's very important to have the facial. IMRCE right now doesn't have a support for facial expression. We are working on the second version of the IMRCE toolkit. In this version, as I said, we are going to have more support, hopefully, for hand tracking, like a controller hand tracking. Also, we are working for matching the different size surface to each other, like a virtual tabletop that can be matched to a different size tabletop. And we are also working for, hopefully in futures, to maybe add some of the different sort of gestures into the toolkit, like new gestures, and also helping people to design new gestures for collaboration. Questions?
Thanks for the speaker. It's good to see these toolkits being developed. Do we have questions? So thank you for the talk. It was pretty interesting.
Thanks.
I've got one question. Why did you build up your own server structure? Why didn't you use something like Photon server? Why did you choose your version? Do you know Photon?
Yes, I know the Photon, the server. So first of all, I think the Unity network, it's the recent, after the update to the Unity version, is very powerful. Even I think it's better than the Photon server. So what we did, we go with the Unity server itself and we customize it for our toolkit. And that's also reduced the size of the toolkit because it's a built-in server of the Unity. When people have the toolkit, it will be much easier to work on, and they don't need really to learn how to work with the Photon server.
Okay, then a second question. Do you also have a voice chat? How do people communicate?
So we don't have the voice chat for this right now. For the study we had, we used the like a normal voice chat applications. That's one thing we should actually consider and add to the toolkit. But right now we don't have a support for the voice chat. Thanks.
Thank you.
Hi, thanks for the talk. I think I have a couple of questions. Maybe I did not catch it. How did you track the hands and what is the accuracy? Did you compare this? And the second question is, when you're working on a small screen, on let's say a Microsoft Surface, and then you're on the multi-touch, are you scaling also the virtual hand to the actual screen size? Because your virtual hand must be bigger then, right?
Right.
Because you're including more content.
So for the hands, we are using the lip sensors. We also a little bit change the algorithm so that be compatible for our toolkit. So mainly it's a lip sensors right now, but as I said, we are working to have the controller and give them more accuracy. And in terms of the resizing, yes, when you are on the like a surface, we also scale down the size of the hands, and based on the location of the hands on the table, we also map it to the right location. But yes, the size will be smaller, so it won't be like occupy the whole screen.
That must be funny when you see like different hand sizes there. You're working with you. Did user comment on this?
If I understand, you mean like...
I mean, yeah, like you have different virtual hands, right? One
Right.
hand might be very big because one guy is working on a small phone or a small tablet.
Oh
you
no,
know?
for example, so if you are on the, the physical tabletop and somebody using the surface, the hand of that person on my physical tabletop will be the size of the hand I have here. So it won't be a small hand here. So we resize the size of the hand based on the screen you have. So if you're on the surface, everybody's hand on your surface will be scaled down.
Okay, thanks.
No worries.
So maybe a follow-up question. So
Please.
you're scaling the hands to fit the physical space, right? So that's the
Into
hands
the
of-
virtual space, yes.
but then if you have the Microsoft or the handheld tablet device, your hand is basically covering the display. And the remote hands are then also
So-
covering content, or?
So it depends you how you put the lip sensor to track your hands. Based on the location of the lip, you can overcome that problem. For example, if you put the surface as like a flat and put this the lip sensor on lower side of it, it shouldn't have a problem. But also you can put the lip sensor on your clothes, so it can detect the hands in front of the surface when you're working on it. It really depends where you want to put the hand, and that's one of the problem I mentioned as a calibration. So people need to calibrate based on the position they want to have the sensors.
Well, I think we were both more focusing on the asymmetry of the setup, so that if you have large-scale displays, small-scale displays, and therefore you need to represent the environment somehow differently, and people will appear at different sizes in the same environment. And that's that's probably something that must be solved for
That's
each
true, yeah.
application. And the question maybe more on the toolkit side is, in the paper you referenced quite a lot of earlier toolkits. And I was wondering, why wouldn't you extend an earlier development, but rather come up with a new toolkit? And from that perspective, how much future do you give your particular toolkit before it will be replaced completely by something else?
So we use the part of the many libraries actually from others developers, and we mentioned that like the libraries for the gestures, and we develop on that. So it wasn't like we designed everything from scratch. I would say the algorithm for hand tracking and also synchronizing hand, that's what we designed from the scratch, and we didn't build up on anything else because we technically didn't find anything that do the hand synchronization between different tools. So technically, I would say what you suggested, it's in the toolkit and we built on those. And for the futures, we will update it based on the update of the Unity, and we are trying to add more features to it. And because of the research ongoing in our labs, I would say it will be going to be a continuous support for these, hopefully for at least a few years, that we are hoping. And hopefully, and that's another reason we put it on the GitHub so people can contribute using, and hopefully people do.
Okay, so let's thank the speaker again. Now we move on to the next talk.